Namaste, and welcome back to JEE Chemistry with Typical Monk. This is Class 24, Coordination Compounds, Part 1. Take a transition metal ion and let molecules and ions crowd around it, each donating a lone pair, and you have a coordination compound, the most colorful and versatile family in chemistry. Werner unlocked them with a single insight. A metal has two kinds of valence, one that holds charge and one that fixes the shape. Today, we learn to name them, count their bonds, and see how the very same formula can hide in two different shapes. One idea at a time. Here is what you will master today. First, Werner's theory and the two valences. Second, the ligands, the coordination number, and the ion rule. Third, the IUPAC nomenclature and oxidation state. Fourth, structural isomerism. And fifth, stereoisomerism, cis and trans, and optical. One idea at a time. Let us set the foundation with Werner's insight. A coordination compound, a central metal ion surrounded by ligands, forming a complex. Werner's two valences. The primary valence, ionizable, satisfied by anions, and the secondary valence, ni-ionizable, which is the coordination number. Ligands, the ions or molecules that donate a lone pair to the metal. Master line, the secondary valence, fixes the geometry, count it, and the shape follows. Now look at the picture. Werner's octahedral complex. The complex, a central metal ion, bonded to 6 ligands in an octahedral shape. Primary valence. The charge in the metal, satisfied by negative ions sitting outside the coordination sphere. Secondary valence. The coordination number, here it is 6, and it is directional, it fixes the geometry. The coordination sphere. The metal and its ligands together, written inside square brackets. Now, the ligands and how many bind. The types: monodentate with 1 donor, bidentate with 2, polydentate with many, and ambidentate. The chelate. A ring formed when a polydentate ligand grips the metal, and it adds extra stability, the chelate effect. The coordination number. The number of donor atoms directly bonded to the metal. The shapes. A coordination number of 6 is octahedral. A coordination number of 4 is tetrahedral or square planar. Now how to name a complex and find its oxidation state. The order. Name the ligands first in alphabetical order and then the metal. The ligand endings. Anionic ligands end in O. Neutral ligands keep their name. Aqua, amine, carbonyl. The metal. If the whole complex is an ion, the metal's name ends in at. The oxidation state. It is shown by a Roman numeral in brackets just after the metal. The ion rule. The effective atomic number equals the metal's own electrons minus its charge plus the electrons donated by the ligands. Now look at the picture. Geometric isomerism, cis and trans. Geometric isomerism. The same formula, but a different arrangement in space. Cis. The two identical ligands sit adjacent to each other at 90 degrees. Trans. The two identical ligands sit opposite each other at 180 degrees. Where it appears. In square planar complexes of the type Ma2B2 and in octahedral complexes. Now, the full family of isomers. Structural isomerism. The same formula, but different connections. Ionization isomers. Swap an ion between inside and outside the coordination sphere. Linkage isomers. An ambidentate ligand binds to a different atom, nitro versus nitrito. Coordination anhydrate isomers. Swapping ligands between two spheres, or water moving in and out of the sphere. Optical isomerism. Non-superimposable mirror images, and they rotate plane polarized light. Now, the 1-mark facts. Werner. The primary valence is the oxidation state. The secondary valence is the coordination number. Stability. Chelates are extra stable, and the ion rule predicts stability near a noble gas electron count. The isomers. Cis and trans is geometric, and mirror images are optical. Now match each term to its meaning. The coordination number goes to Werner's secondary valence. Cis and trans go to geometric isomerism. An ambidentate ligand goes to linkage isomerism. And a non-superimposable mirror image goes to optical isomerism. 4 pairs, each worth memorizing. Now, how many of these statements are correct? Statement 1. The coordination number is Werner's secondary valence. Correct. Statement 2. A chelate makes the complex less stable. Wrong. The chelate effect adds stability. Statement 3. Cis and trans are geometric isomers. Correct. So the answer 2 are correct, statements 1 and 3. The trap is the chelate stability in statement 2. Now the 2 mistakes that quietly cost marks. The truth. The primary valence is the oxidation state. The secondary valence is the coordination number. The trap. Thinking a chelate lowers stability. In fact, the chelate effect raises it. The second truth, geometric isomerism, is cis and trans. Optical isomerism is non-superimposable mirror images. The second trap, naming the metal before the ligands. The ligands always come first in alphabetical order. Now, test yourself. Answer in your head before the reveal. That is how JEE speed is built. Here we go. Question 1. Werner's secondary valence is the coordination number. Question 2. A ligand with 2 donor atoms is bidentate. Question 3. A coordination number of 6 gives which shape? Octahedral. Question 4. Cis and trans are which kind of isomers? Geometric. And question 5. Non-superimposable mirror images are optical isomers. Let us gather it all in one breath. Werner, the primary valence, which is the oxidation state, and the secondary valence, which is the coordination number. Ligands, from monodentate to polydentate, and chelates add stability. Nomenclature, the ligands first, alphabetically, then the metal, and eights for an anionic complex. Structural isomerism, ionization, linkage, coordination, and hydrate. Stereoisomerism, cis and trans, which is geometric and optical mirror images. Next class, the bonding theories, valence bond, and crystal field. Coordination chemistry begins with Werner's 2 valences, one for charge, one for shape, and blossoms into a whole grammar of ligands, coordination numbers, and names. And because geometry now matters, the very same formula can appear as cis or trans, or as a pair of mirror images that no rotation can superimpose. Learn to name them, and to see them in space, and half the inorganic paper is yours. Next class, why these complexes are colored and magnetic, the bonding theories. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack JEE. I will see you in the next class.